back. Hi there. We're going to dig more into the nervous system and nerve conduction and how we get the signals that the nervous system needs to pass across our body to make things work. I'm going to talk about a few more things about graded potentials, then a few things about the action potential, specifically about myelination, and then we'll move on in the next set of lectures to the central nervous system. So just reminding you, all of everything that we're focusing on here is all about electrical conduction. It's all about an electrical signal. We've talked about how a graded potential happens, how an action potential happens, and how a graded potential can be inhibitory or it can be stimulatory, excitatory, and how an action potential is very much all or nothing. So it's not inhibitory or stimulatory. And an important thing when we're talking about graded potentials, another important point, this only applies to graded potential. This does not apply to action potentials. So graded potentials, one of the things in addition to the things that we've been talking about with a graded potential is that they're what's called proportional. So proportional, they're proportional to the strength of the stimulus. And you've probably picked this up already because I've talked about if the stimulus is strong enough, if the stimulus is strong enough, if the stimulus is strong enough, right? Then the graded potential reaches threshold at the axon hillock, and then we get an action potential. So now we're gonna like kind of put that in specifics, I guess. So all this means is exactly probably what you think it means. So if we look at a plot and we have our membrane potential on the y-axis, and then we have our stimulus. So, and this is time down here. And then let's say that we have a stimulus that comes right here. And then this is our membrane potential. I'll do a different color. Our membrane potential is yellow. Membrane potential, remember, we're hanging out negative 70 millivolts. Our stimulus comes, and then we get a change in our membrane potential. Okay. So this is a graded potential. The y-axis is our membrane potential. So as our hump goes up, that means that we're getting more positive. And this is, so we're just looking at excitatory signals right now. This also can apply to inhibitory signals. Okay, so that's our impulse. Cool. So now that's one stimulus. Now let's imagine that we have a stronger stimulus. So if we have a stronger stimulus, in the case of a graded potential, we're going to get a bigger change in membrane potential. That's all that means. It's proportional to the strength of the stimulus. You get a bigger change if you have a stronger stimulus when it comes to a graded potential. Also, what we've already seen, and I'm just going to show you this through another way on this plot, is that our graded potentials can be inhibitory or they can be excitatory. The y excitatory, yeah. Oh, hang on. excitatory. There we go. They can be inhibitory or excitatory, and so same thing, we've got membrane potential over here. And then on our x-axis, we have time. Cool. Same thing, we've got a stimulus that comes, but this time our stimulus is either going to be an inhibitory or excitatory stimulus. And what happens is, if we are coming along and we have an inhibitory stimulus, what's going to happen to the resting membrane potential? We're at negative 70 millivolts. It's actually going to go more negative if in the case of an inhibitory stimulus, inhibitory neurotransmitter. Whereas if we have an excitatory stimulus, we're hanging out at negative 70 millivolts, the resting membrane potential is going to become more positive. That's specific to graded potentials. Action potentials don't do that. Okay. So if we inhibit the neuron, then what kind of polarization would this be right here if we're inhibiting the neuron? Okay. If we're inhibiting the neuron, we're going to hyperpolarize the neuron, whereas what we've been talking about a lot is depolarizing the neuron, right? To get an action potential, we want to depolarize the neuron. So general facts about graded potentials. I'm going to go to a new page. So still talking about graded potentials, we're still in the same wheelhouse. Okay, they lose intensity. As they travel away from the stimulus. Okay, and we saw that with the image that I showed you of the decreasing intensity on both sides, and I related that to your grades, right? You are graded on a graded scale. Okay, these are due to the opening and closing of stimulus gated channels. Okay, how is this different than action potentials? Okay, in action potentials, they're voltage gated channels. All right, due to opening and closing of stimulus gated channels, short distance, this is short distance signaling. And they occur in the cell body. All of this is review. Okay. Again, they can be excitatory or inhibitory. All stuff we've already talked about. Here's the new stuff. They can be summed. What the heck does that mean? If you're doing sums, you're adding. So these potentials can be summed. So what that means is, if we're looking at a neuron that's receiving these signals, it's likely connecting with many other neurons. So we probably have multiple other neurons coming and quote unquote talking to this neuron. It's a complex network. And so what we can get is, you can get the summation we're releasing neurotransmitters. So if these are all releasing neurotransmitters, let's say that 2 neurons are releasing excitatory neurotransmitters. Maybe the signal just from one of those incoming neurons isn't strong enough to produce an action potential. But when both are releasing that excitatory neurotransmitter at the same time, then that's strong enough to produce an action potential. So you can get excitatory plus excitatory. And then that can possibly produce an action potential where you wouldn't have had one from a single incoming neuron, from a single presynaptic neuron releasing neurotransmitter. If you have both, maybe that's then strong enough. Because remember, the strength of the stimulus directly relates to the strength of the graded potential. So you may have guessed, if we can have excitatory neurotransmitters in this synapse that can sum with excitatory, we can also have excitatory that sum with inhibitory. So let's imagine that we have excitatory and inhibitory signals coming in. So then they're competing with each other. So maybe we have excitatory plus inhibitory. And if we add our excitatory and our inhibitory, nothing happens. And so, whereas excitatory plus excitatory, you can think of that as adding two positives. Excitatory plus inhibitory, you can think of that as adding a positive and a negative. And of course, the strength of these is going to play into this too. If the excitatory is super, super strong and the inhibitory is very weak, let's say that this one's really strong and this one's very weak, you might then get an action potential. Okay. So it's important to know that these graded potentials can be summed. So they can be summed across multiple neurons. Those neurons can be sending the same signals. They can all be sending excitatory signals. Some can be sending excitatory and some inhibitory. They can all be sending inhibitory signals, but those can be summed. Another important thing is that these can be summed across. So these can be summed, they can be summed across synapses. So you have multiple synapses receiving information. So that's what that is. That's showing summation across synapses. Another way that they can be summed is across time. I always misspell across. I think it's 1C. Okay, they can also be summed across time or temporally. And so what that means is that if you have you have this presynaptic neuron. Presynaptic neuron A releases its excitatory neurotransmitter into the synaptic cleft. This causes the stimulus-gated sodium channels to open. We've got sodium starts to flood into the cell. We start to produce an excitatory graded potential. Cool. So that happens, sodium's starting to flood into the cell, then that shuts off. And our graded potential starts to move away from the stimulus and it starts to lose strength, because that's just what happens. And let's say very, very soon after, now presynaptic neuron B also releases excitatory neurotransmitter. So the gates, so sodium channels open, sodium floods into the cell, and so its graded potential is coming. And then these two can be summed. So one happened before the other. So you've got one graded potential moving its way, its wave coming down the cell body. and that neurotransmitter's already been shut off, then you have another one that fires, releases its neurotransmitter into the synaptic cleft, into the synapse, causes sodium to flood into the cell. We trigger a second graded potential. And so there's one coming and then the other one's coming. And so those two together can be summed, and maybe together they'll equal that negative 55 millivolts and possibly trigger an action potential. Whereas perhaps one of them alone couldn't. So that's summation. That can also happen same way with excitatory and inhibitory. So you might have an excitatory signal that's going to be strong enough to cause an action potential. It's going to reach negative 55 millivolts at the hillock, at the axon hillock. Remember, the axon hillock is this special spot right here. So maybe you have an excitatory signal that comes in, just like before, but then maybe fix that dendrite. But then maybe the signal from the other presynaptic neuron, it's not excitatory, maybe it's inhibitory. And while this signal was going to be strong enough, it was going to reach negative 55 at the axon hillock, now we have an inhibitory signal, and that inhibitory signal causes that not to happen, and so we don't reach negative 55 at the axon hillock, and we get no action potential. So these are different ways that graded potentials can be summed. Graded potentials can be summed, action potentials cannot be summed. Really, really important point. Action potentials cannot be summed. Okay, so let's just switch our whole, so I was using blue for graded potentials, I'm going to use a kind of orange for action potentials. So we can visually see we're in a different place now. Okay, so these are large, they're uniform, meaning all or nothing, electric signals. Large uniform electric signals, they can travel really far. So remember I told you you have an axon that goes from your hip down all the way down your leg. Okay, so they're large and uniform, they can travel really, really far. So these are due to the opening and closing of voltage gated channels. Voltage gated channels. How is this different than graded potentials? We just talked about this. How is this different than graded potentials? Okay, in graded potentials, we don't have voltage gated channels, we have stimulus gated channels. Go back to my orange. Is that the right color orange? Yeah. Okay. All right. Cool thing, many cool things about action potentials is it's a repeatable, oh, that's not the same color. It's a repeatable depolarization, repolarization cycle. We depolarize, we repolarize, we depolarize, we repolarize, because so that neuron is almost always ready to fire, except when it's in recovery. So we depolarize, repolarize, and then there is a recovery point. There is a recovery period. Okay. So rapid signaling over long distances, these occur in axons, not occur. Okay, occur down the length of the axon, and these are all or nothing. Either it happens or it doesn't. There is no summation. If we reach negative 55 millivolts at the axon hillock, boom, we have an action potential, period. Either it's happening or it's not happening. There's not a more intense action potential or less intense action potential. It is an action potential, period. That's the whole all of it with an action potential. So the sort of next question is, okay, if all we're doing is we're just triggering an action potential, and that action potential is a wave that's gonna go down the length of the neuron, the length of the axon, why does bright light hurt our eyes whereas dim light doesn't? Why do we feel things differently? Why do different amounts of pressure feel different? Why do loud sounds feel different? Why do we perceive those things differently if all we're getting is an action potential, right? Every neuron, that's all it's doing. So you get a stimulus, you get a graded potential. If you get a graded potential, you get an action potential. They do not differ in their intensity. And so we'll talk about that in the next video.